That's probably why. Can you go to the beginning?
I can.
Hello, 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 and welcome to the Denver Astronomical Society channel. My name is Jorge Garcia, and I am your host. Today we have Ron Hranac. He has been the president of the Denver Astronomical Society in previous years, and he usually does this presentation for our community and in public nights. However, due to the COVID-19 situation in which we find ourselves, well, we're trying to reach out to our community via our YouTube channel. I'm sorry for the delay. That was my bad. Ron, take it away.
Thanks, Jorge. All right, take two, as we say. Well, good evening. I'm Ron Hranac, past president of Denver Astronomical Society, and I'm one of the volunteer speakers in our Public Night program. For those of you unfamiliar with our Public Night program, we hold these events every Tuesday and Thursday at DU's historic Chamberlin Observatory. And a typical Public Night event consists of an astronomically themed lecture. I do a presentation on meteorites, and then we follow the lecture with either a tour of the observatory if the weather's not cooperating, or if the weather is cooperating, then attendees get to go upstairs to the dome room and take a peek at objects in the nighttime sky through that fantastic 20-inch Alvin Clark refractor that has hosted many, many thousands of people over the years going back to the late 1800s. Our Public Night program is just one aspect of our public outreach activities, although as Jorge mentioned, given the COVID-19 situation, we're not able to do in-person events right now, so we're doing a virtual Public Night, and I'm sharing with you the presentation that I normally do during the Public Night program, which is to talk about one of my favorite subjects, and that's space rocks, or good old meteorites. And I'm doing this from the collector perspective. I am not a professional geologist. I'm an engineer, but meteorites for me are a fun hobby and a way to enjoy understanding the history of our solar system. Many of you have probably seen meteorites in a museum. In some cases, maybe you never have seen a real meteorite in person. Normally during the Public Night presentation, I pass specimens around the room so people can get some hands-on experience with seeing what meteorites look like up close and how they feel, look at their surface texture and see how they weigh. For example, I have two meteorites here. They're both roughly the same size as each other and about potato size. I love to pass these around the room with the warning, be careful as you pass them from one person to another, because one of them is about twice as heavy as the other, and the weight of this one in particular can get a lot of people by surprise when they're not expecting it. So with that, let me go ahead and begin with tonight's presentation on meteorites, starting with three words that I'd like you to remember if you remember nothing else from tonight's presentation. And the first word is meteoroid. This is the name given to the rocks zipping through space at many, many thousands of miles per hour. Should one of these meteoroids go into an Earth-crossing orbit, it can enter the Earth's atmosphere and become what we call this next term, or I should say produce what we call this next term, and that's meteor. Now, meteor is not the rock itself. A meteor is the streak of light produced by the meteoroid as it plunges through the Earth's atmosphere. And a surprising little bit of trivia, the vast majority of what we call shooting stars, and they're not really stars at all, but what we call shooting or falling stars in the night sky, are produced by meteoroids no bigger than a grain of sand to perhaps the size of a pea. Now, it is possible for much larger meteoroids to produce much brighter meteors. In fact, it's possible for very, very large ones to produce meteors that can be seen in the daytime. And I'll be talking about a very, very famous one a little bit later on in the presentation. Now, there's another little bit of trivia that surprises a lot of people. When you see a shooting star in the night sky, the meteoroid that produces that visible meteor is 50 to 60 to 75 miles above the surface of the Earth. So they're a lot farther away than you might initially think. And then finally, if the meteoroid makes its way through the Earth's atmosphere and reaches the surface of the Earth, then we call it a meteorite. And that's the part I'm going to talk to you about tonight. Now, a quick little side note, The word meteor has its origins going back to about the 1500s or so. And at that time, it referred to pretty much any atmospheric phenomenon. For example, wind, rain, rainbows, hail, all those things were called meteors, along with our familiar shooting stars, of course. And many of you are probably well aware that the person on television who does the weather forecast is called a meteorologist. In that case, a meteorologist is somebody who studies atmospheric phenomena, specifically the weather. Now, there is a name given to scientists who study meteorites, and that name is meteoriticist. And the field of science that they study is called meteoritics. I want to talk briefly about meteor showers because there's oftentimes a lot of confusion about meteor showers and meteorites. An important point here, there is no relationship between meteor showers and meteorites. A meteor shower occurs when the Earth passes through a stream of debris left behind, typically by a comet. So as the Earth, in its orbit around the sun, passes through that stream of debris, that debris, which mostly is dust to sand to pea-sized particles of ice and dust and perhaps some tiny pebbles or rocks, produces the familiar meteor showers that we're used to seeing. There are about 64 confirmed meteor showers and about 300 others that are being studied. The table in the lower right part of the slide shows some of the ones that you're probably more familiar with. For example, the Perseids is a very, very well-known one that occurs in the middle of August every year. And that one, on a dark night where we don't have a bright moon out to obscure the night sky and wash out some of the dimmer meteors, can produce some pretty spectacular shooting stars. And of course, the Leonids are a fun shower, as are the Geminids and the others on here. The showers are typically named after the constellation from which they appear to originate, and that origination point in the sky is known as the shower's radiant. So, for example, the Leonids meteor shower appears to come from the constellation Leo. The Perseids appears to come from the constellation Perseus, and so forth. And as I mentioned a moment ago, meteor showers have nothing to do with meteorites. All right, well, where do meteorites come from? The vast majority come from the asteroid belt. The asteroid belt orbits the sun in between the orbits of Earth and Mars, or rather, Mars and Jupiter. Let me get that right. There are also some asteroids in orbit with Jupiter. They're called the Trojan asteroids that orbit ahead of Jupiter and behind Jupiter in its orbit around the sun. But the bulk of meteorites that we find on the Earth come from the asteroid belt. There are a couple notable exceptions. They're fairly rare, but they do occur, and that is lunar meteorites, yes, meteorites from the moon, and Martian meteorites, and those are meteorites that come from Mars. I'll talk a little bit later on about how scientists know that lunar and Martian meteorites are in fact pieces of the moon and Mars, respectively. Meteoriticists, like most scientists, like to classify meteorites. They like to classify things, and you know, many other scientists like to classify things too: bugs and germs and you know, birds, just about anything you can think of. Well, meteorites are no exception. I'm not going to get into a talk about the classification of meteorites. That would be a presentation all by itself, and one that might not be too interesting, and certainly one that wouldn't do a real good job of keeping you awake. So what I'll do instead is talk about three main categories of meteorites. The first is known as a stony meteorite. This is a stony meteorite, and as its name suggests, it's primarily a chunk of rock, mostly silicates. It does have maybe upwards of 20% or so metallic content with iron nickel mixed into the stone, but it's primarily stone. The second type is an iron meteorite. An example of that is right here. Iron meteorites are probably the ones that most of us are familiar with because that's the type that museums often like to put on public display. And as you can see from the photograph on screen here, this one's got it's got a really nice sculpted looking shape. Those dents, if you will, in the iron meteorite here are called thumbprints, or more accurately, the regmaglyphs, and they're formed as the meteoroid plunges through the Earth's atmosphere, and material ablates off of the meteoroid as it's plunging through the Earth's atmosphere, and it leaves that fantastic sculptured-looking shape. Interestingly, the iron meteorites are fairly rare. the vast majority of meteorites that make it to the surface of the Earth are of the first type, stony meteorites. And then the third type of meteorite is kind of a cross between the first two. It's known as a stony iron meteorite. This picture shows two people you may be familiar with. That's Jeff Notkin and Steve Arnold from the TV show Meteorite Men, which appeared on the Science Channel a few years back. And they're shown here excavating a newly found stony iron meteorite in a field in Kansas. I think this was from a site that they kept fairly secret, but it is a stony iron meteorite. Now, the place in the asteroids where these three types of meteorites originate, in the case of stony meteorite, include the crust of what's called a differentiated asteroid. Now, that would be an asteroid that was big enough when it formed, it had enough gravity to allow, when it was still molten, all the heavy stuff like the iron and nickel to sink to the center and form a core, and the lighter weight material like the silicates formed a crust. So some stony meteorites are from the crust of differentiated asteroids, and many other stony meteorites are from undifferentiated asteroids. Those are ones that were too small to have enough gravity to separate the constituent materials into different layers. So it's all mixed up inside the stony meteorite. The iron meteorites come from the core of differentiated asteroids, and the stony iron meteorites come from the core mantle boundary of differentiated asteroids. So what's inside of one of these things? This particular iron meteorite here is a chunk of what's called the Campo del Cielo meteorite, and if you speak Spanish, you know that that means field of the sky. The Campo del Cielo meteorite is from Argentina, was discovered about 5,000, well, let me rephrase that. It impacted the surface of the Earth in Argentina about 5,000 years ago, but it was likely witnessed by indigenous peoples because they called the resulting meteorite fragments rocks from heaven. So the Campo del Cielo meteorite gives some reference to that, but by virtue of its translation to field of the sky. But the Campo del Cielo meteorite is roughly 92.5% iron, so it makes it very heavy. It's about 6.5% nickel. It's got a little bit of cobalt, phosphorus, and traces of gallium, germanium, and iridium in it. The iridium pretty small in the amount of 3.6 parts per million. Now, something of significance with iridium and the relationship to the dinosaurs is the fact that at the boundary of the Cretaceous Tertiary layers in rocks on the surface of the Earth, there is a layer that's maybe an inch or so thick that has a fairly high concentration of iridium in it, but it's on the order of parts per million, whereas normally in the Earth's crust, iridium is extremely rare, on the order of parts per billion. That layer at the KT boundary, as it's known, is about 66 million years old, and it's some of the leftovers of an asteroid impact that happened about 66 million years ago. Scientists know that iridium is present in higher concentrations in parts per million in comets and asteroids. So that layer at the KT boundary, which has a higher concentration of iridium than the Earth's crust normally does, is kind of the smoking gun that provided evidence for an impact event that contributed to the demise of the dinosaurs. So here's some examples of what some of these other types of meteorites look like on the inside. This first screenshot shows the inside of a stony meteorite, similar to this one, and it's been sliced open. It looks kind of boring because it's mostly gray-looking rock. It has some little white spots in it and little circular spots. Those little circular spots are called chondrules, and those are little spherical-shaped objects that are anywhere from 1 millimeter to a few millimeters in diameter. They're very, very old. They were formed when the solar system formed from molten droplets that solidified and then later accreted into larger rocks that became asteroids that accreted into planets and so on. But the chondrules that are in some of these stony meteorites are responsible for the name ordinary chondrite, the type of stony meteorite that you see on the screen here. The next photo is a picture of a slice of an iron meteorite. As you look at this, you can see an interesting looking crisscross pattern in that image. And the way that pattern is brought out is by slicing an iron meteorite, polishing it, and then etching it with acid. And that brings out the crystalline structure of the iron-nickel matrix inside the iron meteorite. That pattern is called a Wittgenstein pattern. It's also known as a Thomson structure. Both Thomson and Wittgenstein were people who had had discovered the patterns inside of meteorites that look like this. And the third type is a stony iron. As you look at this, you can see it's got a mix of the iron-nickel matrix surrounding olivine crystals. For those of you who have a birthday in the month of August, there's your birthstone. Peridot or peridot is the gemstone variety of the mineral olivine. So some meteorites have the August birthstone in them, as you can see in the picture here. Now, I've talked a little bit about the impact that contributed to the demise of the dinosaurs and the topic of meteoroids, meteors, and meteorites, and the fact that these things hit the Earth. I like to ask the question, how many people have seen the moon through a telescope? And if you have seen the moon through a telescope, you've no doubt noticed that there are a lot of craters on the surface of the moon. Interestingly, the planet Mercury has a lot of craters. Of course, our moon does. Venus has a few. Mars has some craters. The moons of Mars have craters. The moons of Jupiter, Saturn, Uranus, Neptune all have craters. The planet, or well, more accurately, dwarf planet now, Pluto, has craters, as does its moons. And if you think about the fact that many of these solar system bodies have moons, what about the Earth? Where on Earth are all the impact craters? Did the moon perhaps shield us from impacts? And if objects in the rest of the solar system got whacked by asteroids and meteorites, why not the Earth? Hasn't it been hit by objects in the past? And the answer is yes. There is evidence of meteorite impacts on Earth, but what and where? Why don't we see more craters on the Earth? Well, we can thank plate tectonics and volcanism and erosion and Mother Nature in general for covering up and hiding the vast majority of those impact craters. But they have occurred on the Earth, and there are probably 190 or so, or about 190 known impact craters on the surface of the Earth. Arguably the most famous one is the one I show in the picture here. This is one I snapped at Meteor Crater in Arizona. It's about 3/4 of a mile wide and about 600 or so feet deep, out in the middle of the desert, about 45 miles east of Flagstaff, or not too far from Winslow. If you've never seen a impact crater up close, and you happen to be taking a vacation sometime in the future to Arizona, and if you get a chance as you're crossing Interstate 40 in the area of Winslow, take a side turn off the highway and go pay a visit to Meteor Crater. Now, the name is a bit misleading because, as I mentioned earlier in the presentation, the word meteor refers to the streak of light produced by a meteoroid. What they really should have done is called it Meteorite Crater, but it is what it is. So we have Meteor Crater in Arizona. Another bit of evidence of impacts on the Earth is a class of materials called impactites. These are small, often glassy-like objects that are produced as a result of an impact that melts sand or dirt on the ground. The photograph here shows Libyan desert glass, which is found near the border between Libya and Egypt. Libyan desert glass was formed by either an impact or what's called an airburst, that is where a meteoroid or perhaps a comet exploded in the atmosphere above the surface of the Earth and didn't make it to the ground. They've never found a crater yet. What happened was either an impact or an airburst melted sand and made this yellowish-looking material called Libyan desert glass. And it's been known for a long time. The ancient Egyptians made jewelry out of it. In fact, jewelry was found in King Tut's tomb made from Libyan desert glass. Shatter cones are another type of evidence of impact. Shatter cones I like to think of as the fossilized shock waves in the rock. I've got a piece of shatter cone here that I like to pass around the room when I do this presentation at the observatory, and it's got this kind of a grainy looking structure to it, similar to what you see in the photograph on the slide. This particular shatter cone came from near Santa Fe, New Mexico. There's a road cut in I remember if it's a county or a state highway outside of Santa Fe, where the shatter cone is visible. Now, the crater that formed the shatter cone is long since eroded away. Shatter cone tends to form beneath impact craters, but in this case, the shatter cone it remains, but the crater's long gone. And as you look at the picture here, you can get an idea of the size of it. Shatter cone in general can range anywhere from an inch or so high to 10 or 12 feet tall. The examples in the photograph here are maybe 3 feet tall. You can see a geologist's rock pick down in the lower center part of the picture to give you an idea of the scale. But you notice the grainy structure always points up to where the impact occurred. So in this particular example, the grains in the rock point up to where the impact occurred, and then the shock waves propagated throughout the rock and changed the physical structure of the rock, leaving this grainy-looking texture in the rock. And then finally, we have evidence at the microscopic scale. And you may have heard the term shocked quartz. Shocked quartz is found near where atomic bombs blow up, but shocked quartz also can be found around craters where meteorites have impacted the surface of the Earth. And the photograph here shows a piece of coesite, which is a type of shocked quartz. This is the view through a microscope. And then there are microtektites, which are basically melted beads of glass. Now, I didn't mention the tektites under the topic of impactites. Tektites are a type of impact glass, if you will, that take on some really interesting shapes. They can look like teardrops, dog bones, round spheres. Some very rare ones and pricey ones look like buttons. Those have been found in northern Australia, but the tektites in Southeast Asia have been found in an area that covers about 10% of the surface of the Earth. So all over southeastern China and Vietnam and Laos and Cambodia and down into the Philippines and into Australia and some other places in that region. But there was a huge impact. The impact site has not been discovered yet. There are some locations that scientists have been looking at that are potential impact sites, but nonetheless, the tektites from that part of the world are popular with collectors, and most of them are fairly affordable at $10 or so a pop. No talk about meteorites would be complete without at least having a brief discussion about the subject of meteor wrongs. This is not a scientific term by any means. A meteor wrong is a nickname given to an earth rock or a man-made object or mineral or something that is commonly mistaken for a meteorite. And unfortunately, the vast majority of the time, when people find what they think is a meteorite, reality is it's a meteor wrong. Some of the common meteor wrongs that we find in Colorado include hematite and magnetite. Both are types of iron ore. And then, of course, non-rocks such as slag. Slag is a man-made byproduct of the ore smelting process and is very often mistaken for meteorites. Interestingly, slag has been found on every continent on the Earth except Antarctica. It's been found in some of the remotest locations on the Earth where people say, well, nobody smelted anything here. It's been found in deserts. It's been found up on tall mountains. But slag has been a byproduct of smelting processes that have been going on for thousands of years, so it's everywhere. Slag is taken from industrial smelters. It's mixed in with the gravel used in the bedding of railroad tracks. It's used in the aggregate for pavement and other things. So it's not unusual to find pieces of slag just about anywhere. And slag is such a common meteor wrong. And more often than not, people find something they think is a meteorite. And whoops, it's not. It's a meteor wrong. Here are a few more examples. Normally when I do the in-person presentation at Chamberlin Observatory, I have a little display of about 24 meteor wrongs set up on a table. There's one meteorite hidden amongst the meteor wrongs, so people have fun, especially the kids, looking through the meteor wrongs, trying to figure out which one is the meteorite. This particular example shows a piece of vesicular basalt. So think of it as plain old lava rock. You'll notice it's got the little vesicles or bubbles in it. Those are gas-expanded bubbles that form as the magma approaches the surface of the Earth and becomes lava. And as it reaches the surface of the Earth, the dissolved gases in the magma and lava start to expand and make these little bubbles. And people will often think of vesicular basalt as a meteorite because they think, well, don't meteorites have these little bubbles in them? And they confuse the bubbles or the vesicles with the thumbprints or regmaglyphs, and they're not quite the same thing. Obsidian is another one that can be mistaken for a meteorite, although most of the time people realize that, hey, wait a minute, obsidian is volcanic glass. How could you mistake that? And the one in the photograph here, I found in a rock shop when I was on a business trip several years ago. And I looked at the surface texture and thought, this looks kind of like a weathered meteorite. And as soon as you turn it over where you can see it's been cut and there's a conchoidal fracture, it's very obvious that it's not a meteorite, but in fact is obsidian. Magnetite is a very common meteor rong. Magnetite is attracted to a magnet. It can be dark in color. It can be heavy, like many meteorites. But the reality is it's a terrestrial rock, and it's not a meteorite. Here's a piece of slag. Slag comes in all kinds of shapes and sizes and textures. This is a particular one I found somewhere. I don't remember. I think it was in a rock shop someplace. But it's not a meteorite by any stretch of the imagination. Botryoidal hematite. This one has got kind of a bubbly texture, and this is another one I found in a rock shop somewhere years ago. And I thought, people are going to look at this and think it's got that texture traveling through the Earth's atmosphere. And in fact, that's not correct. This formed underground on the Earth. And then the final example I have here is called a Moki marble. It's a little round ball. A hint: the vast majority of meteorites are not round. They take on all kinds of shapes, but round is generally not one of them. Moki marbles form in the sandstone of the southwestern deserts in the United States. Moki marbles are actually iron oxide concretions. So as mineral-laden water makes its way through the sandstone, it can reach an impurity and then start to form a concretion, and these little ball-like objects called Moki marbles form in the sandstone, and then as the sandstone erodes away, these can fall out, and people can sometimes mistake them for meteorites, but in fact, they are not. I mentioned earlier the fact that sometimes if a meteoroid is big enough, it can produce a meteor visible in the daytime. And one such event occurred on Valentine's Day here in Colorado back in 2013. So it was Thursday night, February 14th, at about 8:20 p.m., and that was Mountain Time. It happened to be 9:20 a.m. Friday morning in Russia. Well, at that time, a 65-foot wide, 10,000-ton meteoroid or small asteroid entered the Earth's atmosphere about 40,000 miles per hour. It was big enough that it produced a visible meteor in the daytime. And as you look at the top picture over here, you can see the visible meteor produced by this. Well, when the meteoroid reached a distance from the surface of the Earth of 15 or 20 miles or so, it exploded. Fabulous airburst. And the airburst produced enough energy, probably some of which was ultraviolet light, that some people claimed they got sunburned from the light given off by the airburst. But the shock wave released by the airburst had the energy equivalent to approximately 30 atomic bombs. So people saw this flash, they went to their windows, and about a minute and a half after the airburst, or the flash in the sky, the shock wave from the explosion reached them and blew thousands of windows out of buildings in the city of Chelyabinsk. This city is an industrial city in Russia of about 1 million people. Thousands of buildings were damaged, and around 1,500 people were injured by flying broken glass. Nobody got hit by any fragments or anything of the meteoroid or meteorites themselves, but they were hit by flying glass and were injured that way. And it did cause damage to some buildings. It knocked the wall down on, I think, a zinc factory in one location. And of course, you can see people cleaning up broken glass on the bottom picture here. The explosion or airburst scattered meteorite fragments over a pretty wide strewn field that was several miles away from where the airburst occurred. The strewn field probably at least a few square miles, and the meteorite fragments that were recovered varied in size from pea size, which were picked up off the top of the snow. Remember, this occurred in February of that year, to larger pieces. And you can see in the top right photo, the scientist holding what is that? Maybe a grapefruit-sized chunk of the Chelyabinsk meteorite, and on the paper towel next to his hands, you can see a lot of the pea-sized pieces. The middle picture shows what the inside of this meteorite looks like. It's grayish in color and the texture. The outside is jet black, like charcoal briquettes. That jet black cover is called a fusion crust, and that formed as the meteoroid plunged through the Earth's atmosphere, and it melted the outer millimeter or so of the meteorite. And some of you may have seen the hole in the ice produced by a chunk of that meteorite as it impacted this lake. It took several months before they were able to recover the meteorite that finally did make it through the ice and into the mud down at the bottom of the lake. The meteorite itself was officially classified by scientists, and the name given to it was Chelyabinsk, after the city where it was observed. And it's classified as a stony meteorite, so one of the three main types I talked about earlier. In this case, it's known specifically as an LL5 chondrite. A chondrite, of course, is the name given to a stony meteorite that has chondrules in it. The LL in the classification refers to the fact that the metal content is very, very low, and the 5 is a petrologic rating for how much heating, while the original parent body was in the asteroid belt, changed the interior of the meteorite. Here's a picture on the lower left of the roughly 1 meter wide or 1 yard wide meteorite just after it had been recovered from the mud in that lake. And then on the right side of that, you can see what it looks like after it dried out. And as you can see, the jet black fusion crust is eroded away. This is evidence of what happens when meteorites land in or near water. It doesn't take long for the iron to start breaking down very, very quickly and for these things to start to oxidize. To date, more than 2,000 pounds of fragments have been recovered from the Chelyabinsk area, and they vary from pea size to, well, the one that's in a museum in Russia now, they're the 1 meter size one. Chelyabinsk meteorites are still available on the collector market, so those folks who are interested in getting a piece of a space rock that was witnessed, or it was from a witnessed event, can still find that on the collector market. And speaking of collecting, for those of you who might have an interest in collecting meteorites, the first step is to, well, learn about meteorites. And a good place to start, of course, is with the presentation you're listening to tonight. The International Meteorite Collectors Association has some useful resources on its webpage. The Meteoritical Society, which is a bit more highbrow, I don't know if that's the right term, also has a lot of good references. The Meteoritical Society is an organization to which many meteoriticists and professional scientists belong, as well as hobbyists who follow the studies of meteorites. And then books. There are lots of great books out there. If I had to pick one out of everything shown here as a good all-around reference, the one in the middle, Rocks from Space by Richard Norton, is arguably one of the best. He goes into the science of meteorites and meteoritics, but has a lot of great pictures in the book and talks about the geology of meteorites and where they come from. But it's really an in-depth book. I highly recommend it. The others are of course, are excellent. If you're interested in something a bit more beginner in nature, the book on the far right, What's So Mysterious About Meteorites, which was co-authored by Richard Norton and his wife, Dorothy Norton, is also a great starting point. But the book Rocks from Space, second edition, is the one you should get, is arguably the best all-around book about meteorites. All right, then, if you're going to collect these things, what kind of collection? Well, maybe you start with a very, very simple collection with 3 meteorites in it: a stony meteorite, an iron meteorite, and a stony iron meteorite. Set them up on the fireplace mantle and call it a day. That's fine. So that makes for a nice little collection, and it gives you 3 examples of the main types of meteorites, and they are pretty cool to look at. You can get prepackaged collections. The one shown in the photograph here is from Jeff Notkin's company, Aerolite Meteorites. It includes several meteorite fragments and a couple of impactite fragments. Last time I checked his website, these were going for a little over $200. I think it was about $225, but they come in a nice little box with the labels and the little gem jars with the specimens in them, and it's a nice little prepackaged collection. Now, some people get a little bit more serious about the hobby of collecting space rocks and related pieces and parts. Some collectors like to collect different subcategories. I mentioned earlier that scientists like to classify meteorites, and I've heard of some collectors who like to try to collect all the different classifications that they can, or at least most of them. Some are very, very rare and hard to get. Some like to collect meteorites from specific locations. Colorado, for example, has around 90 confirmed meteorites, either 89 or 90. I think the 90th was just identified just in the last month or two. So some people like to collect meteorites from specific locations, for example, their home state or something like that. Some people like to collect falls versus finds. A find is a meteorite that was just randomly found someplace, while a fall would be like the Chelyabinsk meteorite, one that was witnessed to have fallen. That tends to drive the price up, even though the the specific meteorite type itself might be fairly ordinary in nature, but still the fact that it was witnessed can increase the price. Another type is hammerstones. Hammerstone is a nickname given to meteorites that impacted something like a house or a garage or car or ship or whatever, but mailbox, and yes, a mailbox has been hit by a meteorite. The Claxton meteorite from Georgia. It was a witness fall. It hit a meteor or hit a mailbox. Get this, the mailbox sold for $82,000. Yikes. Some people like to collect thin sections. Those are meteorites that have been sliced very thin, cemented to a slide for a microscope, and then they grind down that specimen even thinner to just 30 microns, that's 30 millionths of a meter. And then people like to look at those through polarizing light microscopes. And, in fact, geologists used to use polarizing light microscopes to identify mineral content in rocks and minerals and meteorites. These days they use fancy instruments like X-ray fluorescence spectroscopy and electron beam microprobe machines and other things that can identify what's going on down even to 2 microns or less in size. Some people like to collect impactites, and there are people that like to collect meteor rocks. So where do you get them? Well, you can buy meteorites at some rock shops, although my experience is that rock shops tend to be a little bit on the pricey side. You can find them on online auction sites. There are legitimate dealers of meteorites online. Just be careful. On some of these auction sites, you may find that there are unscrupulous dealers who are peddling ordinary earth rocks as meteorites, or maybe peddling ordinary meteorites as extremely rare ones. And if you don't know the seller online or in these auction sites, I encourage you to at least start with those who are members of the International Meteorite Collectors Association. I've got a list of some online dealers and some websites here. I won't read through all these, but you can see these. These are all dealers that I've dealt with over the years. They're reputable businesses. They're run by people who have been selling meteorites for a long time. Here in Denver, we've got a couple places online. Mile High Meteorites is run by Matt Morgan, who's a professional geologist, and Impactica is run by Ann Black, who's one of the most well-known meteorite dealers in the world. She happens to be right here in Denver as well. And then, of course, there are rock and mineral shows. Denver hosts 2 fairly good-sized rock and mineral shows, one in the spring. Unfortunately, this year's spring show had to be canceled because of the COVID-19 situation. The fall show is the big one. The fall show is held each year in September. This year it's scheduled for September 10th through the 20th. Interestingly, the Denver show in the fall is the 2nd largest rock and mineral show in the United States, and it's the 3rd or 4th largest in the world. It takes place in multiple venues. I think something like a dozen different venues that include the Merchandise Mart and the National Western Complex and the Denver Coliseum and a lot of different hotels and other places. And I've been known to take 4 or 5 days of vacation just to wander around the fall show, just to see the rocks and minerals on display. And of course, both the spring and fall shows also attract meteorite dealers. So it's a good place to look through real meteorites up close and maybe get something that might appeal to your eye to add to your collection. All right, let's go through some common questions. How big are meteorites? And like so many things, this is one of those "it depends" answers, but they can range in size from smaller than a pea to bigger than a car. The biggest known meteorite on Earth is the Hoba meteorite in Namibia, Africa. It weighs about 60 tons and is roughly 9 feet by 9 feet by 3 feet. In the picture here, you can see a guy standing on it. That's where it was found. I think it was dug up, but they built some little circular kind of places to sit, to watch, to take a look at this. But the Hoba meteorite is where it was found. Big meteorite, but that's the biggest one that's known. Are they radioactive? Now, this is a question I have fun with, because during my normal public night presentation, I pass specimens around the room among the attendees, and I ask this question: are they radioactive? Of course, I ask this after I've been passing specimens around the room for the previous 30 or 40 minutes or so. Well, the answer is no more than your hand. we can thank Hollywood for the myth that if a meteorite lands in your backyard, that you're going to grow 15 arms and 3 heads, and the night crawlers in your lawn are going to turn into giants. No, that's nonsense. So they're no more radioactive than your hand or your foot. How old are meteorites? Well, the vast majority of meteorites are a little over 4.5 billion with a B years old. Meteorites, for example, like this, are older than any existing Earth rock. All the rocks on Earth have been recycled over the years through plate tectonics and volcanism and other natural phenomena and processes. But meteorites are leftovers from the formation of the solar system. The asteroid belt at one time was thought to be the remnants of a small planet that had broken up somehow, perhaps in a collision, and then wound up orbiting the sun between Mars and Jupiter. And in fact, scientists now know that the asteroid belt is basically leftover pieces and parts from the formation of the solar system. So they love to study meteorites because they provide a real good opportunity to look at some pristine rocks left over from the formation of our solar system a little over 4.5 billion years ago. Earlier I mentioned that hammerstones are meteorites that hit something like a house or a barn or a car or a mailbox. All of those have actually been hit by a meteorite. What do you think? Do you think a person has ever been hit by a meteorite? And I'll pause there for a minute and just let you think about it for a second. What do you think? All right. The answer is yes. There's at least one documented instance of a person being hit by a meteorite. This happened to a woman named Ann Hodges in Sylacauga, Alabama, back in November of 1954. She was laying down on the couch in her living room in Sylacauga, and a meteorite about the size of a softball, maybe a grapefruit, crashed through the ceiling of the room, bounced off of a radio, and then hit her. And you can see in the picture on the left where she was hit on the hip. No broken bones or anything, thank goodness, just a really nasty bruise. She got her picture in Life magazine at the time, and then here in the picture on the right, you can see her holding the meteorite. You can see the hole that's left in the ceiling of the living room, and she's standing there with a police officer and some other person. An interesting story behind this: she was a renter of the house, and there was some question about the ownership of the meteorite. The landlord said, "Hey, I own the house, so I own the meteorite," and she said, "Well, I got hit by it, I own it." And there was a bit of a well, shall we say, disagreement over who should own the meteorite. I think eventually she and her husband wound up with it, but they were never able to sell it for some reason, and it wound up in the Natural History Museum in the capital of Alabama. There was another meteorite that is related to the one that impacted her house and her. It hit the land. It was found in the ditch alongside the road about I want to say a quarter mile or a half mile from her house. So what happened was a meteoroid entered the Earth's atmosphere and probably broke into a couple pieces, and the one piece landed in the road a little ways away from her house, and the other piece crashed through the roof of her house and then hit her. The one that landed down the road does occasionally, well, that specific one doesn't, but tiny pieces of it occasionally show up on the collector's market, but it's extremely rare and very, very hard to get. Well, do meteorites contain any mysterious or unknown ingredients? For those of you who are fans of X-Men, and in particular Wolverine, my apology, you may be aware that it's a material called adamantium that strengthens his bones and it gives him some of the power that he's got. In the movie, or the X-Men movie that showed Wolverine in it, the adamantium that was eventually injected into his bones and turned him into really super strong, call it superstructure, if you will, supposedly came from a meteorite. Well, the reality is there's no such thing as adamantium. The pieces and parts that make up meteorites are the same things you'll find here on Earth: iron and nickel and silicates and so on. You may find that some meteorites contain fairly rare elements. For example, iridium is fairly rare on the surface of the Earth or on the crust of the Earth. That can be found in some meteorites, and in some cases, some meteorites do contain previously unknown minerals. For example, there's one called wassenite, named after a very famous meteoriticist by the name of John Wasson. This is a titanium sulfide It's extremely unstable in the presence of oxygen and moisture and tends to break down extremely quickly in Earth's atmosphere. So it's been found in microscopic amounts in some meteorites, but it's very rare. In space, it does fine because it's a vacuum, but once it gets exposed to oxygen and moisture, it tends to oxidize very, very quickly and break down quickly. All right, so how do scientists know that lunar and Martian meteorites actually are from the Moon and Mars? And I should probably start by answering the question, well, how on earth would a chunk of the Moon or a chunk of Mars make its way to Earth as a meteorite in the first place? And the answer is that in the past, asteroids whacked the Moon and whacked Mars with enough energy to blast crustal material into space at a velocity that exceeded the escape velocity for the Moon and Mars, respectively. Some of those pieces made it into Earth-crossing orbits and then wound up on the surface of the Earth as lunar and Martian meteorites. Now, in the case of lunar meteorites, they have a composition very similar to the rocks brought back to Earth by the Apollo astronauts. Some Martian meteorites were found to contain microscopic bubbles of trapped gas. And when scientists analyzed that gas, they found that it contained Martian atmosphere. And I think the first Martian meteorite was confirmed in about 1984 or so. We had sent probes to Mars in the 1970s and had landed on the surface of Mars and had sampled the atmosphere. So if you've got a meteorite with microscopic bubbles of Martian atmosphere embedded in it, it could only come from one place, Mars. And scientists believe what happened is as the incoming asteroid impacted the surface of Mars, it compressed some of the atmosphere in front of the asteroid, and that wound its way up in the molten crustal material that was later ejected into space. And then as it solidified, the Martian gases or the atmospheric gases in tiny bubbles were trapped inside the rock. And then we found pieces of those on the Earth and did the analysis and said, okay, that's where they came from. And then here's some information about the isotope ratios that scientists have measured in lunar and Martian meteorites for those of you who are interested in a little bit more about the chemistry of these things. All right, here's a fun question. How many meteorites hit the Earth every year? And I probably should have worded this question a little bit differently, but here's the answer. An estimated 60,000 tons of meteorites whack the Earth every year, which works out to an estimated, count-wise, 18,000 to 84,000 meteorites. Now, you have to realize that about 70% of the surface of the Earth is covered by water, so that means that statistically speaking, about 70% of the meteoroids that plunge through the Earth's atmosphere and make it to the surface wind up in the drink. They don't wind up on solid land, which is unfortunate. And the question everybody likes to know the answer to, how much do these things cost? The answer is another one of those, it depends. Meteorites sell by the gram, and it's possible to buy low-cost, inexpensive Northwest Africa unclassified meteorite specimens for anywhere from 10 cents a gram to 50 cents a gram or so. You can spend as much as several $1,000s per gram for certain extremely rare meteorites. But a good middle-of-the-road number, figure $1 to $10 a gram for decent quality meteorites. And here I'm talking about meteorite fragments from Meteor Crater in Arizona and other meteorites that people like to collect. So that gives you an idea. The price is all over the place, but you can get some really good ones for that $1 to $1.10. All right, that concludes my part of the presentation. So let's see if you have any questions that I've not covered in tonight's presentation.
Yes, let's go back into the questions and answers. Oh, wow. So let's look at some of the questions posted in the chat. We have from Dina. She asked about the Atlas comet, and if whenever it break up, if we could have a meteor shower created from that breakup.
If the remnants of the comet produced a debris trail that crossed Earth's orbit, then it could be possible. I have not heard that is going to be the case, so I'm guessing that that's not likely going to happen. I think that it's too far away from the Earth for us to plow through a debris stream left behind by that comet. So I doubt that we're going to see a meteor shower as a result of that.
Ed Ladner was asking, is the Gulf of Mexico a crater?
The Gulf of Mexico is not a crater. However, the impact site for the asteroid that wiped out the dinosaurs 66 million years ago was very close to it. It occurred on the tip of the Yucatan Peninsula, producing a crater about 150 miles wide. That crater is known, I think the pronunciation is Chicxulub event, was discovered by geologists a few years back. I think they were doing gravitational measurements looking for oil deposits or something, and they found call it the fossilized remnants, if you will, of a very, very old crater, and they've already drilled core samples out of it, and they've confirmed that its age is about 66 million years, and they've also confirmed that the boundary or the layer of material at the KT boundary is thicker as one gets closer to the Gulf of Mexico. So that says very strongly that at least that impact. By the way, the asteroid that created that crater was about the size of Mount Everest, so roughly between 6 and 10 miles in size. But no, the Gulf of Mexico itself is not a crater, but a crater does exist just off the tip of the Yucatan Peninsula, but it's a lot smaller than the Gulf of Mexico. Good question.
Hey, Ron, can you also quit sharing your screen so we can see you a little bit bigger?
All right.
There you go.
Oh, so I look the same as I did, but instead of a little picture, I guess it's a bigger picture.
Oh, yeah.
So, other question?
Yes, Robin P. asked, I want to know where I should look for meteorites, or if there are
that's a real good question and a very common question. Where should one look for meteorites? And the answer is probably the easiest place to look for meteorites is at the rock and mineral shows that I mentioned. That's where you're most likely going to find them, and rock shops and that sort of thing. Going outside in the expanses of the wild, the places to look include known strewn fields. So you need to find out where meteorites have been found before and go look there. Those are good places to look. Other good places include some of the dry lake beds in Utah, Nevada, California. Those can be good places to hunt for meteorites because they tend to be light colored, and the meteorites can stand out a bit on the surface of those dry lakes and a little bit easier to find. Deserts are definitely much better places to try to find meteorites than, say, mountainous areas or jungles or other places where you've got heavy forest, because quite frankly, those places tend to obscure and hide the meteorites. They're very, very hard to find. If you look at a map of meteorites that have been found in the state of Colorado, you'll see that the vast majority have been found in the eastern half of the state, in the plains, mostly on ranches and farms, or they've been found by farmers and ranchers as they plow fields and so on. A few have been found in the mountains, but there aren't too many. So find known strewn fields in areas where meteorites have been found in the past. Those are some of the best places to look. A good place, for example, is for the Holbrook meteorite, which can be found near Holbrook, Arizona. And that event occurred in the early part of the 20th century. I forget, around 1910 or thereabouts. People were sitting down to eat dinner, and the meteoroid exploded in the atmosphere and rained down thousands of fragments over the town of Holbrook. And people still find meteorite fragments to this day. There's an area on the one edge of the town where people go look, and they still can find them there occasionally. Not as often as they used to, but they still do show up there. So those are the best places to look for meteorites.
So let me see. I'm scrolling through the chat to see if anybody else posted any more questions. Somebody said, shout out to my dad, Robert, tuning in all the way from Florida. So hello to Florida.
Hello to Florida from Colorado. Yes, thank you for joining us.
Condor 996 says, very cool presentation. Would love to see this live someday.
Well, thanks for the kind words. If you look on our, well, once we get back into the in-person meeting situation, then when the public night program does resume at Chamberlin Observatory, take a look at the calendar on our website. There's a public night. There's a way you can go up into the corner of the thing and pick I think it's a view that shows I forget the exact wording on it, but it lets you show which teams are doing public night presentations. I'm a member of Public Night Team 1, and if I'm not out of town on a business trip, then I'm usually there as part of Team 1, and I do the presentation on meteorites before the observing starts in the observatory.
Ed Ladner asks, would a satellite entering the atmosphere be a meteor? And parts
Technically, the answer is yes. Keeping in mind that a meteor is a word that describes a visible streak of light in the Earth's atmosphere. Space junk, as it's commonly called, entering the Earth's atmosphere, the spent rocket stages and satellites that have been deorbited, that sort of thing, do produce what is technically known as a meteor in the night sky. And if it's big enough, maybe in the day sky, but usually in the night sky. They're usually pretty easy to tell apart from a true meteoroid that's entering the Earth's atmosphere at 40,000 miles an hour.
Oh, very nice. We have Red Rendache watching from the Philippines. Hi, Red.
Oh, very good. Welcome to the Philippines to our event tonight. Thanks for joining us.
Tony saying good tips for finding any meteorite.
Good tips? Well, the first thing to do is learn about meteorites, and it's important to learn what they look like. So spend some time in a museum if there's one near you that has meteorites on display. Get to a rock and mineral show or a rock shop where you can get some hands-on with some meteorites. And that way you get familiar with what they look like. But read up on them. There's some videos online. Just be careful. There's some bogus videos that show fake meteorites, but there's some good websites online that include examples of what the real things look like. So it's important to understand what they look like so that when you get out into the woods or wherever you're looking for them, you'll have a better idea. And you should also become familiar with what some of the meteor rongs look like. Take a look at pictures of slag and volcanic rock and lava and some of the other things that are commonly mistaken for meteorites. Many people use a magnet to see if a specimen is a good candidate, and the reason they do that is because most meteorites contain iron, and that means that most meteorites will be attracted to a magnet. But a magnet test is not a reliable indicator that a meteorite or a given specimen is a meteorite, because many terrestrial rocks and minerals are also attracted to magnets. So while it might help narrow the field down, it's definitely not proof positive that the specimen is a meteorite, because so many terrestrial rocks are also attracted to magnets. But I'd say get to a museum and rock shops and other things where you can see real meteorites up close and see what they really look like. And then you can use that information as you go out looking for them.
We have Robin P. Is Chesapeake Bay a meteorite crater?
Which one? Chesapeake Bay?
Chesapeake, I guess, yeah.
There is I think it's Chesapeake Bay, either in Chesapeake Bay or near Chesapeake Bay, I think is a known impact site.
Oh, nice. So I think that's it for tonight. I don't see any more questions coming in. Ron, thank you very much for sharing all your knowledge.
My pleasure, and I'd like to thank everybody who joined us this evening for the presentation, and hope to see you sometime soon in person at the EU's historic Chamberlin Observatory. Have a very good evening.
Thank you very much, guys. Have a good night. Okay.
Are we clear?